Hey everyone, I'm Sudhava Yadav from Department of Physics, Malvern National Institute of Technology, Jaipur, India. I want to thank the organizers of Cosmology from Home 2024 for giving me chance to present my work entitled Reheating Dynamics of Logarithmic-Corrected Quadratic Information. So here's the outline of my talk. First, I will be giving the brief introduction to reheating, then reheating parameterization, where the parameterization which we have used to do the reheating dynamics study, then the potential which we have used for our study, the results and conclusions. So moving to the introduction part. So first, the initial stage of our universe, that observable universe, and its evolution was governed by two basic phenomena, that is cosmic inflation and Big Bang nucleosynthesis. So first one, this inflationary dynamics, inflationary phase. So this inflationary phase came up with an aid to resolve the well-known cosmological problems of homogeneity, flatness, and monopole. Then the Big Bang nucleosynthesis. The Big Bang nucleosynthesis successfully produces all the light elements with the correct abundance values. So these two phenomena actually happens at two different separate energy ranges. So the inflationary phase occurs at 10 to the power 16 giga electron volt, and then this Big Bang nucleosynthesis happens around at a lower energy scale, that is around 10 mega electron volt. So there is no actually there's no well-established physics to understand the phase in between the two. So the process that could have occurred is the transfer of inflated energy into the standard model field. So the phase where this energy transfer from inflating to radiation happens is called reheating. So now coming to the parameterization part. So this is the reheating parameterization methodology used for the work. So we assume that the universe is dominated by a fluid with energy density U, that is proportional to the pressure, and this constant equating constant is effective equation of state parameters, that is omega effect. And we analyze the dynamics of inflation by considering a scalar hypothetical field phi, and the potential associated with this inflated field is the V phi, that is the potential. And this inflated field phi is assumed to evolve slowly with the slow roll parameters epsilon and eta. These are the two slow roll parameters, and these are written in terms of this potential. Then the famous Friedman equation is written using this slow roll approximation, and this gives the condition for this Hubble parameter. And the Hubble parameter can be written as x equal to v pi by 3 mp square. Then the three more parameters, that are the scalar spectral index ns, that the tensor to scalar ratio r, and the tensor spectral index nt, are written in terms of these slow roll parameters, that as ns equal to 1 minus 6 epsilon plus 2 neta, and then nt equal to minus 2 epsilon and r equal to 16 epsilon. Then moving to this to one more parameter, that is the number of e-folds, that is the duration we can call. The number of e-folds between the, we assume a mode k, some mode k, and the number of e-folds between the time when this mode k crosses the Hubble radius to the end of inflation, and end of inflation, which is denoted by the subscript n. And the number of e-folds can be written as the logarithmic ratio of a n by ak, that where a is the scale factor at the end of inflation, and this is the scale factor when the key crosses the Hubble radius. And then that can be further written as 1 by mp square and integration from pi n to phi k b by b dash, and where mp is the reduced Planck mass. Now, these are the two key parameters governing the reheating phase. The first one is the reheating temperature TRE, and the second one is the duration of reheating, that is NRH. So these two parameters are written in terms of late time observables and average equation of state omega effective, and there are various different parameters used that are. That one is GRE, that denotes the effective number of relativistic species at the end of reheating, and then the Z equivalent and the rho equivalent. These are the redshift and energy density at the epoch of matter radiation equality. And the parameter k by e naught is the observed wave number of any physical scale today. So these are the two key equations which we will be using in for our study. Now coming to our potential. So it is a V pi, the normal chaotic potential, that is half m square phi square only. So this is the logarithmic correction added in the mass term. that is k ln phi square by mp square, where mp is the reduced Planck mass and k is some positive constant denoting the coupling of inflated dominance of coupling of inflating to the fermionic fields. So on the right-hand side, you can see the plot, a plot showing the potential versus phi. So first, I will be discussing the field domain within which this inflationary phenomena occurs for this potential. So it is evident that this potential does not exhibit this positive definiteness for all values of phi. So it becomes negative after a specific value that can be seen from this plot also. So also this model has a sense provided that the this correction term does not have its dominance over the whole potential. Hence, the suitable regime chosen for our work is phi less than this phi top, and that should be less than this phi v equal to phi at v equal to 0. So we will be working in this potential region. Now, as I have shown in the earlier slides, these parameters are written in terms of V pi, but we will be just substituting the value of this potential V pi on those equations, and we can easily get these parametric equations from those by the direct substitution and little rearrangement. So these are the equation for the two Slorol parameters. Then this is scalar spectral index written in terms of of inflated field and the potential parameter K. Then this number of equals written. So here the end of inflation, the condition of end of inflation we will be using. So the condition for end of inflation, that is the first Slorol parameter goes to 1 equal to 1. So by using that equation, by using that condition, we can obtain the value of phi n, and we will be using that value here to get the remaining number of equals from the crossing of bubble radius by k star to the termination of inflationary epoch. The k star is we can say just like we have used a normal k. This is k star, same thing. So after that, to just make the things little easier, we have just substituted phi star by np as x, so that the equations were little neat and easy. So then the two more parameters, that is center to scalar ratio and the Hubble parameter h star. These are also written in terms of this inflated field energy. Then one more parameter, that is the potential at the end of inflation, that is also written in terms of this inflated field at the end of inflation. Now, putting all these equations putting all these equations which we have got in these two equations, this ln TRH and RE, after putting those values in these key equations, we can easily obtain the plots of NRH and TRH versus NS. So here are the plots. And for the potential parameter K, we have used 4 different values of K equal to 0.13 to ranging from K equal to 0.13 to 0.16. So these are the 4 plots for 4 different values of K. So from the plot, you can see that there are different shades of color shades. So different colors demarcates different color curves demarcate different values of omega R, that is effective equation of state, ranging from -1/3 to 1. And here, the gray color lines, this gray color contours, these are the Planck plus BK18 contours, and we can say bounds on NS value. That is 0. This dark gray one is 1 sigma bound on NS value, and this light gray one is the 2 sigma bound on NS value. So this gray one, dark gray one is 1 sigma limit, that is 0.966 plus minus 0.004 used by us. So after that, this one, after from these plots, we can say this figure illustrates the point where all these plots, all these curves for different omega RE converges this point, and this demarcates the instantaneous reheating, and the temperature is maximum here, and this temperature is independent of omega R. For all omega R, this is same. So, and from this plots, we can see for the values k equal to 0.13, 0.14, and 0.15, these curves are well within the compatible range, we can say, for accepting the values, negative values of omega RE. But for 0.16, we can see directly, we can clearly see for point k equal to 0.16, this the curves for k equal to 0.16 shows the incompatibility with data for all values of effective equation of state. So irrespective of any value of omega are you taken, these curves are completely outside the compatible range. So we have to restrict ourselves for values k less than 0.16 for us to take. So now coming to the this tabular data. So by demanding TRH, the reheating temperature greater than and equal to 100 gigaelectron volt from here. Demanding TRE greater than or equal to 100 gigaelectron volt for the production of weak scale dark matter. The permissible range obtained for NS, Talens, and R for different values of K are tabulated here. So these are for K equal to 0.13, 0.14, 0.15, and 0.16. So these are the NS value, NS range, and these are the Talens star range, and these are the R range. So these NS and R values from here, we have plotted in a plot, a separate plot, so to show the things nicely. So this is the tabular data, our tabular data, and then this is the conclusive plot. So from this plot, you can see, first I will be tallying these contours. This dark and light blue shading correspond to the 1 sigma and 2 sigma bounds from Planck 2018 plus BK18 plus BO data. And the limit of NS, 1 sigma and 2 sigma contours of NS are already told. And the R value, the limit on R value is R less than 0.036 we have used. And these different values of these curves, different values in the curves are the different omega RE ranges taken. So it is well mentioned in the caption. So now we have used 4 different values of K. And okay, then now coming to the K equal to 0. So we from the plot, from the potential, okay, from the potential, we can see if we will put K equal to 0, then we will directly get this normal quadratic chaotic inflation, that is half m square pi square. So I have plotted that also with the plots of this 4 values, so that we can see what is the change happened due to the corrective term. So for K equal to 0, we can directly see that is this is showing complete incompatibility with the data, observable satellite data. And after doing the correction, this is lying within the range. So for K equal to 0.15, it can be seen for omega RE greater than 1/6. This curve is coming inside the range. So after that, conclusions of our work. So, by imposing the reheating conditions on this model, we found that the constraint or NS and R are consistent with Planck 2018 plus BK18 data for K values closer to this K equal to 0.15. And after that, the range of omega reached for which our obtained data is compatible with Planck 2 sigma bound on NS and R gives us omega R lying in the range 0.7 to 1 for K equal to 0.15. Then the reheating study shows that the value of K close to 0.15 are the more favorable ones, and the omega RE range, this range satisfying the observational data for K equal to 0.15 suggests the production of dark matter particles, that are feebly interactive massive particles SWIM, and weakly interactive massive particles, that is SWIM. And also there may be a production of primordial black holes. So the elaborated study of the type of particle products produced and the related study of reheating with particle production will be done in our future publications and will be discussed then only. So then the findings of conclusively we can say the findings of reheating study proves that even a small correction in the potential in the mass term of the potential, normal quadratic chaotic potential, help the quadratic chaotic potential to favor the observational data well. And the reheating study effectively narrows the model viable parameter space. That is, we can say the values closer to equal to 0.15 are the best ones. So in general, we can say that the reheating study effectively narrows the model viable parameter space and significantly improves the accuracy of model, giving us the more efficient models. Thank you.